have something pretty cool for you today because we just got finished with Oktoberfest celebrations. It is still October, of course. So in honor of Oktoberfest, we took a visit to Stone Brewing Company, which happens to be, just down the street from us here in the studio. And we had a head brewer there named Mitch. He gave us a nice tour, and he showed us all these ways that math came up in the brewing process, which I was quite surprised at. But I will follow it up a little bit. I'll show you how the math shows up. But first, check out the little tour we got and check out what Mitch had to tell us about Stone Brewing Company. I am Mathman Dan. We are at Stone Brewing Company with their head brewer, Mitch. And Mitch is going to try and convince me that there's math used in making beer. And I don't know much about it myself, so I'm getting educated here as well. But we're starting the process right here. So Mitch, what is happening in this bin?
Well, this is the first step in what we call the brew house process, which is the hot side of the brewing process. Basically a big kitchen that we have here. And what we do in this tank here, this is called a mash kettle. And what we do is we mix a specific amount of malted barley with water to create a mixture that's somewhat like oatmeal. And part of the math that goes into that is calculating the amount of malt that we want to use to get a certain sugar percentage at the end of the process.
Does that depend on what kind of beer you're making at the time?
Exactly. It depends on what we're making, how much alcohol we want to make. And if we use, say, 10,000 pounds of malt, we know we're going to get a beer out of this brewery that's probably going to have about 10% alcohol.
Okay.
So there's a lot of simple ratios that we use in the brewing process to figure out if we have a starting sugar content of 10%, we're going to end up with an alcohol content of 4.2%. So the starting sugar content we multiply by 0.42, and it's a reflection of the chemical equation for fermentation.
And that tells you how much you're going to put in here to start the process?
Exactly.
Okay, and then when this is done mixing around, then what happens?
Well, we mix it around for a certain amount of time to get the sugars that we want, and we extract all the sugars out of the malt. And then we take this whole tank, the contents of this whole tank, and we transfer it over to this next tank here.
All right, so this one's much hotter, I can tell.
Yeah, what we're doing is we're boiling the liquid here. This is called the wort kettle, and to me this is the most important part of the brew house process. And this is where we add the hops to the brew house process, to the wort. And adding hops are one of the 4 primary ingredients in beer, and hops contribute bitterness to the beer, which balances out the sweetness from the malt. So it's and our beers tend to be fairly bitter in flavor. And what we do is when the hops come in, they're given a rating, an alpha acid content percentage, and usually it's 5 to 15%. And from that contributes, it's a direct ratio to the amount of bitterness we get to the wort. So if the hops come in with a 15% alpha acid content, we can calculate to get 40, 50 bitterness units in the beer, which is a chemical analysis, and it's a measure of how bitter the beer is.
Okay, so you're always measuring what's the ratio you want, and then again you're adjusting.
Exactly. There's a lot of variables that go into that IBU calculation. There is the strength of the hops themselves is measured by the alpha acid content, the strength of the wort. There's also a number here that we use called the utilization percentage. So usually with whole hops you get 25% utilization. With pellet hops, which is what we use, you get 35% utilization. And there's a lot of different numbers there, but the end result is your bitterness value in the wort, which is measured by a lab.
Okay.
And we can adjust the hopping based on what we're trying to get as far as the bitterness level. If we're getting 40 IBUs or international bitterness units and then one brew gets 35, we know that we might need to make an adjustment in our hopping because we're not getting the same utilization.
You showed me, I saw earlier, a big formula in your office. Is that what this is?
That's exactly what that is.
We're going to have to show that formula later.
Okay. So the wort here is boiled for 90 minutes, and that allows full extraction of the hop bittering compounds out of the hop material.
Okay. And once it's done boiling, what do you do with it?
Once it's done boiling, then we transfer it down to this next tank here. We boil for 90 minutes, and we're looking for a certain evaporation percentage measured by the sugar strength in the wort. So typically we're looking for a 6% evaporation, and we compare the sugar content before and after the boil.
So that's something you're monitoring?
Yeah, and we'll actually change the boil time to make sure that we get the proper evaporation here.
So Mitch, what is going on here?
Well, this is our fermenting cellar, and every one of these tanks is a fermenter. And we put the wort that we create in the brew house into these tanks, and this is where we add the 4th ingredient in beer, which is yeast. Now, yeast is interesting because it's a living organism, and it's what's producing the alcohol and the carbon dioxide, which gives the beer its foam. And that is a process where the yeast eats the sugars that we create in the brew house and forms alcohol and CO2 as byproducts consuming that sugar.
So you guys add the yeast yourselves at this point, and then you just let it sit here for a while.
That's exactly right. What we do is when we pump the wort into this tank, we meter in the yeast so that we get a cell count, which is something that we measure at the initial filling of the tank and then during stages of the fermentation. And a cell count we measure in millions of yeast cells per milliliter of wort, and it's done in the lab. And what we do is we pull a sample off of this tank and then we put it onto a special plate and look at it under a microscope and simply count with a counter. And then we can translate
with your eyeballs, you sit there and count them.
Exactly. And then we do a multiplication to get millions of cells per milliliters from that count.
Okay, so you're taking a ratio there and just kind of extrapolating it up to the full amount of liquid.
That's exactly right. Because what's going to happen in here is the yeast is going to start feeding on the sugar, and yeast reproduce by budding. So we're going to see some logarithmic growth with the yeast. And so if we start off at a cell count of 18 million cells per milliliter at the start of the fermentation, at the height of the fermentation, the yeast are going to reproduce enough to give us a cell count of maybe 120 million cells per milliliter. Okay. And then at the end of the process, as most of the sugar is consumed, most of the alcohol is produced, the yeast will start settling out into this cone, and this cone is the precise angle to help yeast really settle out of the rest of the beer.
So they settle down, and then you told me that you guys actually do more than one process of fermentation. You do a second stage? Or?
Yeah, we divide the process into two stages. The first one is the primary fermentation at 70 degrees Fahrenheit, and this is where the yeast consume most of the sugars, produce most of the alcohol and the carbon dioxide. And then as those sugars are consumed and the yeast starts to settle out, we start chilling the tank down, and then we go through an aging process. It's either 5 to 7 days depending on the beer, and we hold the beer at 35 degrees, and the yeast settles out some more and matures the flavors in the beer. There's some other flavor maturation things that go on to make the beer really taste like beer at the end of the process.
So how long is it in these tanks total before you're done with it?
10 to 15 days typically. It depends on the brand of beer.
And then you ship it off and it's ready to go?
Yep. Yeah, we'll filter it, we'll run it through a filter, and then we'll put it in a package and it's out the door.
Mitch, a lot more math and physics actually than I would have expected in the making of beer. So thank you so much for your time today.
Yeah, you're welcome.
And back in the studio, we're going to see a little bit of how some of this math came into play. You know, our good friend Mitch there, he actually mentioned a whole bunch of mathematical concepts when he was showing us around Stone Brewing. I'll mention just a few of these that I spotted. So he talked about calculating the amounts of ingredients to mix when they make the beer. He talked about measuring for the desired sugar content, and that in turn leads to the amount of alcohol content they want in the beer. And he said different varieties of beers have different amounts of that they have to measure for. He talked about a chemical equation for fermentation. He also mentioned calculating evaporation rates when they were doing this. They talked about evaluating the temperatures and also the pressures. And a couple other things that were brought up. I don't know if you saw that crazy equation for bitterness. I actually put on my math cams. I wanted to show you what all that stuff was standing for. We've put it on the screen a couple times. So if you look at my math cam here, I wrote it up for you. This is the IBU calculation. This is International Bitterness Units. It's a measure of how bitter the beer is, and that's determined by how much of the hops they put in. And this equation establishes a connection between everything. So the W was for the weight of the hops in ounces. U was what Mitch referred to as the utilization percentage. This alpha percent here, this is the alpha acid content of the hops, so they have different ratings. The 7489 is for converting the units. We have the volume below in gallons, and we have C, it says gravity. This is the specific gravity, which is basically the density of the hops compared to water. Now, by using this formula, they have a desired bitterness they want to hit, and then they can sort of work backwards and figure out how much of the hops to put in for whatever kind of beer they're making. And he told me it varies with different sorts of beers that they're doing. He also mentioned, he used the word logarithmic. I don't know if you caught that, but he was talking about how the yeast grows. And depending on how you look at it, whether you're measuring, you know, sort of like from front back or back to front, is logarithmic or exponential. He mentioned that the yeast actually bud and reproduce, and he talked about them going from 18 million to about 120 million cells per milliliter. So there's actually a formula for this. This is basically exponential growth that the yeast is doing. And this is a standard formula from a math class. So this is C is the initial quantity you'd use, T is the time, and in this case it would probably be days they'd measure it in, and K is the growth rate, and you can determine that either experimentally or from some biological knowledge of how the yeast reproduce. One last thing I was going to show you, we did flash a quick equation on the screen when he talked about how they measure how much the yeast content is, and he said they actually go in a microscope and count them. So what he's doing to do this is a simple ratio or proportion, and it's really easy to do, and there's a lot of applications for proportions like this. So I was going to show you a quick one on my math cam here. I made up an example. I don't have exact numbers from Mitch, but this is the idea of what he was doing. So let's say you go on your microscope and you put some of your mixture on the slide down there, and you look through your microscope and you're actually sitting there counting yeast cells. And I make up a hypothetical example here, but it should be similar to what he would have to do. Let's say you had 82 yeast cells. I'm going to make a little fraction here, and I'm just going to compare the number of cells to how much, well, it's not exactly water, but the mixture I have under my microscope. And it's going to have to be a pretty small amount. You've got to think if you're having a little squashed amount of material you're looking at on your microscope, it's not going to be very much. So I made up a hypothetical situation, but I have a very small amount of liquid here. There's 5 zeros I'm drawing there, milliliters. And what we're going to do, this is how a proportion always works. This here is a ratio, and to make the proportion work, you set it equal to another ratio that has the same quantities represented in it. Now, the units that they used for the yeast measurement was millions of yeast cells per milliliter. So what I want to know is if this is the ratio that's happening under my microscope, how many of those cells would I expect in 1 milliliter? And the proportion always makes sure that these stay in sync with each other. So all we could do is just say, okay, well, I don't know how many cells are in a milliliter yet. I'll just call it X. Then we're going to go ahead and figure out what X would have to be. So basically we have two ratios equal to each other. That makes a proportion. And anything you can think of that sticks at the same rate, you can always set up a proportion to solve little problems like this. So once you set it up, how do you solve such a thing? There is a nice little algebraic shortcut you can use. It's called cross-multiplying. Always works if you have just two fractions equal to each other like this. What you can do is multiply the diagonal ones here. So I'll put 82 times 1 and multiply the opposite diagonals. So this is 0.000004 times x. Those have to be equal. This is sort of a shortcut for more official algebraic technique, but as long as you have one fraction on each side, it always works. All you got to do next is a little computation. I'm just going to divide both sides by that decimal number. And if you go on a calculator and figure this out, it comes out to be, I did it ahead of time so you don't have to watch me push the buttons, 20,500,000. So we would say that the yeast concentration in this mixture would be 20.5 million cells per milliliter. So he mentioned this goes all the way up to 120 million, so 6 times more than this. We had a good time touring Stone Brewery, and if you guys are local, I don't know if you eat at restaurants out around here, you'll notice that their beer is pretty popular. Well, they actually have a whole restaurant facility attached to where they make the beer, and from the restaurant you can actually look through this big glass wall and see all the stuff they're doing in there. And the food's good, and it's a great place to be. So if you're in Escondido, you should stop by. It's a good time, and we enjoyed getting a little tour from Mitch. So thank him for that. Mathman Dan here. You know I like to show you how math gets used out in the real world. And so we are out in the field today, and actually today we're meeting with Craig Boyd, and we are at Mount Palomar Winery, and you are their winemaker.
Correct.
And there's all kinds of math being used in winemaking, which I wasn't even aware of. But first of all, in addition to making me look short, you are going to show me some math that I'm not aware of. So
yes, yeah, it's a little technique we use for blending, and it's called a Pearson's square. Very, very simple.
Pearson's square. All right,
Pearson's square. So take a square, and if you have two wines, say I have two wines I want to blend, one is 17% alcohol, one is 10% alcohol.
Okay.
And I want the final product to be 14% alcohol.
Okay.
All I do is go across the corner and take the difference between these two, and I have 4 there, and the difference coming this way, and I have 3 there, and that tells me that I have 3 parts of 10% to 4 parts of 17% will give me 14%.
You mix those together, you will get 14%.
Right. And a 4-to-3 ratio.
Works every time.
Works every time.
All
And
right,
we use it on a multiple number of different things too.
I'm going to
not just
have to
alcohol.
investigate this further. All right, you also told me you use genuine algebra. You wrote an equation for me a few minutes ago, right on paper. And that also was for mixtures.
Right.
So you were, if I remember right, you were taking a certain amount of alcohol level of wine and trying to figure out how much additional of another kind of wine to get a certain percentage.
Yep.
So the equation I saw looked just like what we call mixture problems.
Exactly.
And it looked just like something my students would have on their homework or an exam. So I'm actually going to follow up. If I remember right, it was like you took 750 milliliters of a wine and tried to figure out how much
with a
more.
known alcohol and added, and I'm going to add a different alcohol wine to it with an unknown quantity, X.
It's called X, right?
And then end up with the final product, which will be the 2 quantities combined at a known alcohol, what I want. And
all right,
solve for X, simple algebra, do it all the time.
So when we're actually back in the studio, I'm going to solve that problem, write down the equations, to convince the students that actually you are using their exact algebra problem right here in your day-to-day job. All right. You also brought a book with you that had all kinds of stuff, and I flipped through it briefly. But
yes, we do a lot of chemistry. There's a lot of chemistry involved in winemaking.
Okay.
Art and chemistry. It's a neat mix of that. And this is a book. It's full of all the chemical analysis we do, and almost every one of them has a formula involved.
You actually use these day-to-day
all
basis?
all the time. You can see, look how worn out the book is.
That's true.
It does get quite a bit of use.
So what kind of things would you use? Are you measuring certain levels?
Yeah, if we're measuring acidity, if we're measuring sugar, if we're measuring pretty much any chemical component of the wine, we have a formula for it and we can do it using math.
You're actually putting things in these formulas in general. Okay. And finally, you told me you have to do some conversions, and that happens a lot in math classes and other science classes. But you were mentioning that these are actually measured in metric.
Yes.
So this barrel, for example.
225 liters. The bottles are 750 milliliters. So everything pretty much is kept in liters. But our government doesn't want us to report all the reports we do. Have to be done in gallons.
Figures.
So we do a lot of converting back and forth between gallons and liters, between metric and English, and in the lab too, because a lot of the experiments are done in grams, and occasionally we'll be adding in pounds. So we do a lot of converting back and forth.
Do you have those numbers in your head?
Oh, absolutely.
Greg,
3.785 liters in a gallon.
There you
or gallons
go.
a liter. Back
I'm
liters in a
convinced.
gallon. Yep.
This has been very interesting, and I had no idea there was this much math involved in your day-to-day job, but thank you very much for sharing that with
You're
us.
welcome.
And I'll look forward to having a little sample a little later.
Okay, sounds good.
So our friend Craig there, he was actually really fun to talk to because he has a scientific background, and he was, trying to show me how this all goes into winemaking. And so he mentioned some, things like converting units, and that comes up a lot. We actually did that last week in an algebra problem. And he also talked about all these chemistry formulas he used. I flipped through his book. There's, tons of formulas, of course, with chemistry that might make sense. And maybe you didn't realize how much chemistry goes into making a decent wine, but he convinced me. And then he also talked about some algebra stuff. And for one thing, he did this quick little computation on the side of the wine barrel there. I'll show you that a little later, but what he was doing there. He also mentioned a genuine algebra problem. And I said, it sounded just like what you would see in classes we teach here. And sure enough, it looks like you could have plucked it right out of an algebra book. Well, I was going to show you that algebra problem. So you can think of this two ways. It's kind of like doing double duty here. On the one hand, this is a math problem that our friend works on almost every day when he does his job. And also, this is a little practice for you if you are in an algebra class and you have to do one of those, so-called word problems that I know everyone likes so much. So it's an example called a mixture problem. It's exactly what he was doing. I wrote up a problem on my little math chem here. So we're going to pretend like this is right out of an algebra book, and we'll see how we can tackle this. Maybe this will help you algebra students out there. And it's also, what this guy has to do when he makes wine every day. So the problem is he mentioned, I'm going to use the same percentages he actually mentioned here. See if you can read that. It says how much wine containing 17% alcohol should be mixed with 750 milliliters of wine containing 10%. You can mix this stuff together, and you want to end up with a 14% alcohol solution. So if you're in an algebra class, I'll show you how we would set this up. And this is pretty much what he was doing at his job as well. And maybe, I don't know if you're in algebra class, if you do this regularly with these problems, but you often make a little grid. So let's do that, just to help to organize things. You don't actually have to do this, but I'm going to make a little grid here. And we're going to label this with the three things we're playing with. So hold on. So I'm going to remove the problem out of there. Hopefully you got that in your head, the numbers we've got. I've got, let's say, I don't know, wine number 1 here. And we've got wine number 2. And then I had the mixture. So the mix is what's going to happen when we put these two guys together. So what I want you to think about with this problem is the things we have to figure out is how much of each one we're going to use. We know the percentages. And then to figure the problem out, we actually compute literally how much alcohol is in each mix, like as if you could separate it out. I know we can't really do that, but that's kind of what we're going to do. So the first column, we're going to put how much wine you have. The second column will be the percentage. And the third column, this will be the amount of alcohol you actually have, measured as a volume of liquid. So think about the relationship here. You're taking a percentage. So all you have to do is multiply the percentage by the amount, and you will get how much alcohol is in each amount of liquid we have. So the way he said it was, we're going to do 750 milliliters of the first wine, and that was 10% rather. So I'm going to write 10% as a decimal. So normally when you actually compute things with percentages, you treat them as a decimal or a fraction. So I'm going to put 0.10 for 10%. And then the question is, how much 17% alcohol should we add? So we don't know. Let's call this something generic, like, oh, how about X? That's everyone's favorite, right? So we'll call it X. That was 17% alcohol. And then when we mix the stuff together, we want to end up with 14% alcohol. So the rest of this we're going to fill in with, well, we're just going to use a little common sense here. If you have 750 milliliters and you have X more milliliters, and we don't know how much X is, but still we're going to put this all together, then the combined amount is just going to have to be 750 plus X. Okay, how about that third column there? Well, I don't want you to think of writing any equations or anything yet. The third column we're going to fill in just by the relationship I wrote on top of the grid, which is multiplying these things. So we're going to multiply the percentages by how much we have of each liquid, and that'll tell us the net amount of alcohol in each one. So 750 times 0.10 gives you 75. So we're multiplying this across and seeing how much that equals. Do that to each row, even if you have variables. So this one is going to be X times 0.17. So I'll just put 0.17X. Third column, be a little careful on this one. I'm going to have to, actually I'm going to need a little more room here. What goes in here is 0.14 times 750 plus X. All right, 0.14, we need to distribute this. 0.14 times 750, I cheated, I did it ahead of time. It's 105, and that's plus 0.14X. So look at all the stuff we filled in here, and you can think of this as we're just kind of, organizing information. I didn't solve anything yet, and I haven't set up anything to solve it. What you have to do now is write an equation to solve. And to do that, all you have to do is look at that third column, and again, we're going to use some common sense here. This is the amount of alcohol in the first part, this is the amount in the second part, and this is the amount in the mixture. Well, those have to combine up and equal the third amount. We have separated the alcohol from the first wine, the amount from the second. We're going to combine it all. It has to total the amount in the third, which is the mixture. So just by thinking about what has to total up here, we're going to have 75 plus 0.17. That's the amount in the second wine. That has to equal the amount in the mixture. And now you set up a little algebra problem that you can solve. So for a moment, you can kind of, forget where all this came from. Just work on solving the question or the equation. And we figure out what X is. We will come back and see what that actually gives us. So a little solving here. Let's get the X stuff on the same side. So how about we ditch the 75? That would make 0.17X. That would be 30 plus 0.14X. So if you've taken some algebra, remember all these little rules we can do. Let's get the 0.14X off of the left side, or the right side. So let's subtract it from both sides. Okay, now on the left, that gives me, let's see, 0.03X. And on the right, I get 30. Last but not least, I want you to get rid of the 0.03. So we're going to divide both sides by 0.03. And 30 divided by 0.03 is exactly 1,000. So that is the answer to our question. If you look back at my grid, what X represented, that was how much of the second wine we needed, and it turns out we need 1,000 milliliters. So think about this just for a moment. We were combining 10% and 17% wine, and we got 14. Now 14 is right in the middle of 10 and 17, so you might have thought, oh, it's maybe, well, not perfectly in the middle, but it's almost. You might have thought like kind of even amounts of each. Well, not quite. It's 750 of the first one, and 1,000 milliliters. You actually need more of the 17 to get it up to 14.